Okay, so sec, cosec, and cotan, which is what we learnt last time. Remember, sec is 1 over cos, cosec is 1 over sine, cot is 1 over tan, which most of the time you can just treat as cos over sine, because tan is normally sine over cos. And what we're going to talk about now is the good old-fashioned core 2 stuff, which is proving identities, simplifications. And obviously you don't have to write this down if you don't want, because you can just watch the video later. Simplifications and solving equations. Okay, so this is totally core 2 revision, girls. Everything I'm going to teach you now is just core 2 stuff with these new 3 fellas. Okay, so let's do proving identities. Okay, so an example would be this fella, cot theta cosec theta over sec squared theta plus cosec squared theta equals cos 3 theta. Okay, and whenever you prove an identity, you have to obey a certain rules of setting it out. Now, the reason why these rules apply is because this is not an equation that you're trying to solve. You're trying to prove that this is the case. So you're saying no matter what theta is, this is equal to that. When this is 5, this is 5. When this is 2, this is 2. When this is math error, this is math error. They're just exactly the same. And there's a symbol that we use to remind you that you're not trying to solve an equation, it's this fella. That means that it's exactly the same as. It's basically an identity rather than an equation. Because it's not an equation, you must not do red dudes. So you must not multiply both sides by sec squared theta plus cosec squared theta. Were you explained last year why you can't do that? Huh?
Is that the straight jacket?
Well, I called it the straight jacket, but I'm talking about why. Why can you not do red dudes on this when you're trying to prove it? Huh?
So changing it?
Okay, what I just said, because that'd change it, that's not the right answer. The whole point of red dudes is that they did not change it. Back in the day when you did this, the whole point is that you were just changing the way it looked. So the red dudes did not change it. They just changed its appearance. Imagine like I tell you you're going to get some chocolates and you say how many. This is the least annoying answer. I just say 3. But on a day when I'm annoying and you go, how many chocolates am I going to get? I say, oh, if you double the number of chocolates and add 1, you get 7. And you go, would you just shut up and tell me how many chocolates I'm going to get? These 3 things say the same thing, right? And that's why red dudes work. It's because if this is true, this is true. If this is true, this is true. If this is true, this is true, etc. Okay? I'll tell you, the reason why you must not do red dudes is because when you do red dudes, you're assuming that it's true and coming up with another version of it. So even if it's false, you can do that. That's false. That's false. That's false. Yeah? They're all equivalent versions of saying the same false thing. Because x is not 3.5. Or is it? Bad example. Oh yeah, sorry, if I was lying to you, so you're not going to get 3.5 chocolates, these are all equally good versions of the lie. Okay, and what tells you that is that it's perfect year 8 red dudes between them. Okay, so don't do red dudes on this. You're not assuming that it's true, you're trying to prove it's true. And therefore you have to go into this straitjacket, which Dad talked about. The straitjacket is to make a choice. Would you rather turn this into this or this into this? Turning this into this goes against the grain that you've been in for 7 years, which is to make complicated things simple, not simple things complicated. So the best choice, I think, is to turn this into this, and the straitjacket is to use this notation device. You name this, very simple, you just call it the left-hand side, and you then do a mixture of algebra manipulations and trigonometric tricks, substitutions on this until it becomes... So, what should we do first? Should we do an algebra manipulation? We could just swap the order of the bottom, but that's kind of lame. What can we do, Joanna? Should we just say what these fellas are? Why don't we do that? Yeah? So cot theta is cos theta over sine theta. cosec theta is 1 over sine theta. Now I don't like crowding my brain out too much, so I'm a big fan of just wasting a bit of ink, copying out something until I'm ready to deal with it. Don't use dittos. Okay? Now, so that was trigonometric substitution. This next thing is just the fractions wrap, top times top, bottom times bottom. Yeah? And now I think that I can safely start working with that. I don't think it'll crowd out my brain too much if I do that. So let's say that this is 1 over cos theta squared plus 1 over sine theta squared. Just got to be patient. You copy out the top. I don't know why I wrote them like that. Okay. So what should I do now? Should I do trigonometry or should I do algebra? What's your call, Emma Smith? You got any clever thoughts? Hmm? Yeah, let's do something with the bottom. What should we do? It's not an equation. We just got to muck around with it like it's algebra. Back in the day, you know, 1 over a plus 1 over b. What'd you do with it? You just added them, right? You made a common denominator. Yeah, so the common denominator would have been an a plus b, yeah? So it would have become b over ab plus a over ab equals b plus a over ab. These are more complicated than those, but there's no reason why we can't do it. So let's do that. What's our common denominator going to be? It's going to be the product of those. Is everyone cool with what I'm doing here? Yeah, we happy with that? Gabby, can you guess what I'm going to do?
Write them together as one fraction. So they're the same denominator, so write the bottom together as one fraction.
Yep. You really have to be very patient with this, girls, and you also have to be flexible. Sometimes you get down a complete dead end. You have to cut your losses, go back to the start, or go back a couple of steps up.